I welcome you to today's ECT Star introductory colloquium on the science topics of the workshop Nuclear Physics Meets Condensed Matter, Symmetry, Topology, and Gauge. This workshop was planned originally for 2020, but has been deferred to 2021 because of the COVID-19 pandemic. It'll focus on the quantum mechanics of many body systems, bringing together nuclear and condensed matter physicists to discuss common topics in few body systems and in the quantum many-body problem. As you know, the intention of this colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's talk will be given by Joaquin Drut from the University of North Carolina at Chapel Hill. Let me briefly introduce Professor Drut. He was born and raised in Argentina, where he studied physics at the University of La Plata, graduating in 2002. In 2003, he moved to the University of Washington, where he obtained his PhD in 2008. He was a postdoctoral researcher at Ohio State University and at Los Alamos National Laboratory, ultimately moving to the University of North Carolina in 2012. Since his PhD studies, Joaquin has been interested in the quantum many-body problem with a focus on universal systems at the interface between atomic and nuclear physics. For his work, he has received several awards and prizes. Joaquin, thanks very much for agreeing to give this talk.
Right. Today, I want to talk to you about challenges and advances at the interface of nuclear, atomic, and condensed matter physics. And I want to thank the organizers of the workshop, Nuclear Physics Meets Condensed Matter, Symmetry, Topology, and Gauge, for giving me the opportunity to give this colloquium talk. And I'm looking forward to participating in this workshop in the future when we can all travel again and meet each other in Trento. This is the outline of my talk. I will give you a short introduction and then mention some of the challenging systems at this interface between atomic, nuclear, and condensed matter physics. I will explain the nature of the difficulty and say a few words about what we can do about it, and then present some selected results and a new idea. And finally, I will summarize and conclude. And I'd like to start by mentioning my group here at UNC, which I like to call the Computational Quantum Matter Group. And our tagline is that we study the structure of strongly coupled matter in extreme environments. And I will say a few words about what that means for us. Currently, we have 3 graduate students in the group. And the main person involved in the results I will show today is Yachi Ho, who is in his 5th year. But also Caitlin Morel and Alex Cheto have participated in some of the work as well. And what do we mean by quantum matter and more generally by computational quantum matter and all that is written here on this slide? In brief, quantum matter means that we're interested in systems of many particles governed by the laws of quantum mechanics. We also are specifically interested in systems that are strongly coupled in some sense. And what that means very generally is that interactions are essential. That is, they're not a small contribution. And so we want to tackle these systems in a non-perturbative way. Furthermore, we're interested in extreme environments, that is, situations that have extreme temperatures and densities. And I'll clarify and give you some examples of what I mean by that in the next 2 slides. Finally, computational, of course, means what you would expect, which is that we use computers to explore new approximations and algorithms and to try to calculate the properties of these systems of quantum matter in strongly coupled regimes and in extreme environments. And for this crowd, I think the types of systems that are represented by these conditions really don't need much of an introduction. There are examples of quantum matter in strongly coupled regimes in a variety of areas across physics, in fact, all over physics. And shown here are simply some pictures indicating some of those areas. One of them is, of course, nuclear physics, astrophysics directly connected to to nuclear physics. Of course, QCD, but also more on the condensed matter side of the story. For example, ultra-cold atoms, graphene, and certain types of superconductors. Going specifically to the nuclear case, here the many particles are, of course, neutrons and protons. And in this case, you have spin and isospin, and that makes a very, very rich situation, and the interactions are also quite complicated. And I will just leave it at that. I will not say a lot about the interactions, but they really make for a very challenging problem. In fact, if you really want to understand the nuclei across the nuclear chart, shown here as number of neutrons on the horizontal axis and number of protons on the vertical axis, then you really face a very difficult challenge. In fact, if you focus on this region of the nuclear chart, then you can point out which nuclei we have been able to tackle and which ones we haven't, I mean, as a community. And that's shown here in this chart that I got from Heiko Hergert, who published it recently on this reference. And shown here are the nuclei that have been tackled with ab initio methods, specifically those for which the community has been able to calculate the ground state energy and other basic properties like that. And as you can see here, up until about 2010, the situation was rather dire. So only a few nuclei had been analyzed or have been available with ab initio methods. And by the way, by ab initio methods, of course, we mean a situation where you specify which particles you have and what your Hamiltonian is, and then you just put that whole thing into a many-body method, and with no other approximations. Now, I remember very well when I became faculty in 2012 that also at that time, not a lot had been done, but quite a bit has been done since then. So it's been basically 10 years since the beginning of this chart, and now there's hope that one can push much further into the nuclear chart. Now, to even understand where these nuclei come from, let alone the structure and reactions, if you really want to understand where they come from, you really want to understand what happens in the neutron-rich part of this chart, and you really need to look at astrophysics. So that in that case, you really want to understand what happens to nuclear matter. And in fact, you want to know what happens when not only in the ground state, but also at finite temperature. And that's the type of situation that you encounter in astrophysical objects like pulsars, at the center of which there will be a neutron star. And we want to understand what happens inside a neutron star, but also what happens when neutron stars collide and merge. And these neutron star mergers are extremely violent objects, situations, and that disrupt the structure of space-time and create gravitational waves, which, as you all know, are detected here on Earth. Now, again, if you really want to understand where nuclei come from and what happens in these violent collisions and how the structure of stars and the properties of matter inside stars affect the gravitational waves that we detect, then you really want to understand nuclear matter. And that's also a very challenging problem because, again, you have many particles and you have strong interactions. And in this case, it's even more complicated because at low densities, you will have neutrons and protons and dominating the picture. But as you increase the densities, you go more towards a quark type of picture. And that then becomes full-fledged quantum chromodynamics, which, of course, is very, very difficult to tackle. And I will come back to that in a few slides. Now, for a lot of this talk, I will be focusing actually in the other direction. I will be focusing on the regime where you have dilute system of nucleons. And more specifically, I will be thinking about dilute neutron matter, which for the purposes of this talk will be characterized by just these two numbers, scattering length and range of the interaction. And this is a very interesting regime because it's directly connected to systems that can be realized with ultra-cold atoms. So this is now a completely different scale where you have a scattering length that instead of being measured in Fermi is measured in Bohr radii, and a range that similarly instead of being measured in Fermi is measured in Bohr radii. So it's a huge difference, several orders of magnitude difference in length scale. And by the way, if you come from an area of physics where you're not used to thinking about scattering lengths and such, you can think about the situation as being such that there's a short range interaction that gives you some kind of square well potential. If you want, then the depth of this potential is essentially represented by the scattering length. That's of course not really what it is, but for the purposes of this talk, that'll be enough. In these situations where you have dilute neutral matter or dilute atoms in this regime where the scattering length is much larger than the range of the interaction, then the physics is governed by this idealized situation where you have infinite scattering length and zero range. And that's what we call the unitary limit. And at that point, this square well potential is essentially tuned to the point where you're just at the threshold of bound state formation for two particles. That case is completely governed by this simple Hamiltonian, where you have a non-relativistic dispersion relation. So this is just p squared over 2m. There's nothing else in that. And you have a contact interaction between spin up and spin down, and you only have these two particle species up and down. In the case of cold atoms, it will be pseudo spin. Of course, in the case of neutrons, it will be actual spin. And for a lot of what's going to happen in this talk, we're interested in analyzing the behavior of this Hamiltonian when there are many particles and when they are at finite temperature and possibly at finite polarization as well, when you have more particles type up than down or vice versa. In ultra cold atom experiments, this is actually very easily realized. And in fact, experimentalists can explore this whole so-called BCS-BEC crossover shown here in this phase diagram, where you have temperature in the vertical axis and coupling in the horizontal axis. And in terms of this dimensionless quantity shown here in terms of the scattering length and the Fermi momentum, which essentially is the density, you get the non-interacting regime all the way to the left, far left. That'll be non-interacting. As soon as you turn on an attractive interaction, you enter this BCS regime where at low enough temperatures you form large overlapping pairs where the size of the pair, of the Cooper pair, is much larger than the interparticle distance. If you keep increasing the strength of the interaction, at some point you will reach that unitary point where you form a two-body bound state, and you enter this this area that's generally called the unitary regime. And if you keep increasing the coupling, then you will go towards a Bose-Einstein condensation type of superfluid, where effectively your degrees of freedom are simply dimers, very compact dimers. So as I said, we'll be interested in finite temperature, the finite temperature situation, but also we want to know what happens when you turn on a difference in chemical potential between spin up and spin down. That is to say, we're interested in finite polarization. And again, this is a situation that can be realized in experiments. And I want to say a few words about that because whereas on the nuclear physics side, you get whatever couplings you get, and you get whatever densities you get inside a neutron star. On the atomic physics side, you really have a lot of control over all these parameters, and that makes these systems really fascinating. Experimentalists can control the temperature and access superfluid transitions. They can control the polarization, as I said before, and certainly the coupling by tuning a magnetic field. This is well known at this point. They can control the shape of the external trapping potential, and this is useful for the theory side because they can realize systems that live in 2D or effectively in 1D by simply constraining the trap in various dimensions. And what that gives you is the ability to do calculations quickly on the theory side in lower dimensions and then compare with the experimental side. Not only can all these systems be realized, but also experimentalists can measure a variety of properties going from thermodynamics all the way to entanglement. And so why then are all these tough problems challenging? That's part of the premise of this talk, is that there are all these systems at the interface between, in this case, atomic and nuclear physics, but they're challenging to study. So why are these challenging? And in many ways, this community, again, doesn't need much of a reminder of why these problems are challenging. But for the sake of completeness, I like to talk a little bit about that. So why is many-body physics so challenging? And at the most basic level, we have problems that actually are not challenging, that we can solve, like the classical two-particle problem of the Earth going around the sun, or if you want, the moon going around the Earth. And of course, that's been solved a long time ago by Newton. And if you want to add more particles, it's really not much of a problem. There are situations that are challenging when you add more particles, but generally you can say, well, NASA has been solving the problem of planets going around the sun for a long time, and the computers we have today really don't find much of a problem in having n particles for large n. People in the area of astronomy also use n-body simulations for a variety of applications. So that's not really much of a problem. Things get more complicated when we go to the quantum two-particle problem. Although, again, this is a problem that we solve either as advanced undergrads or graduate students. We all solve this problem, and we know from there that this is really not the right picture. That is, that the hydrogen atom is not just an electron going around a proton, that in reality, things look more like this. We have some kind of electronic cloud around a proton, and that is a result of solving a partial differential equation. And that's where things start to get a little bit more challenging. If you want to add more particles, then it's not so simple. And the picture that emerges from this, which I will talk about in more detail in just a bit, is that the computational cost as a function of particle number really has an exponential wall for quantum systems and is much milder for classical systems. So where does this come from? Why is this so much harder for quantum mechanics than for classical mechanics? And you can trace that back all the way to the Schrödinger equation, of course. This is the Schrödinger equation that we learn in as undergrads or in graduate school. And of course, this is the one particle Schrödinger equation. This is what perhaps we're not reminded of enough. When you add one more particle, things quickly get more complicated. Every time you add a particle, in fact, you add 3 more dimensions to your wave function and to your differential equation. And so every time you add something else, then things get substantially more complicated each time. And the heart of the problem is really in the interaction. If we didn't have an interaction, then of course we would be able to solve this problem quite easily. We all know how to solve for free particles. The matter is really that these two coordinates are all linked together by this interaction. In this case, a 2-body interaction. And of course, it gets much more complicated when you have 3-body interactions and such. But already here, we realize that from a computational standpoint, merely storing this object in memory is a really bad idea. If you had 10 points for each coordinate that you want to put in here, then you will have, even in one dimension, you have 10 to the n points that you would have to save in memory for n particles. And that's just too much information. That blows up exponentially. So we have a memory problem. And then you can ask the question, okay, well, what can we do about it? And what we learn now as more advanced students at PhD level is that there is a way to tackle this problem, especially if you're interested in finite temperature, where you really reformulate the quantum many-body problem, and you, instead of focusing on a wave function, you focus on the quantities that you want to study. Or if you want, you reformulate the problem using second quantization, field theory, or Green's functions, however you want to call it. And one of the perhaps modern ways to see this is via field integrals. And so I want to say a few words about that. And again, I'm going to be focusing on these types of expressions under field integral forms because we're interested in finite temperature quantities like a density equation of state or like a pressure equation of state. If ultimately we want to apply this to a challenging problem like neutron matter or nuclear matter as present in a neutron star. So of course, this is just a cartoon, and the real thing looks more like this. So the expectation value of your operator now is written as a complicated object or a complicated looking object. And so let's unpack that. In this expression, you have on the right-hand side a normalization, which will typically be your partition function, of course. You have an action that encodes your physical situations, so the system and whatever parameters come with it, chemical potentials and temperatures and such. I mean, temperature, singular, and such. And then your observable quantity, which is whatever you want to study, either a density or again, some correlation function or response function, what have you. That would go here. The complicated part of the situation is here, the sum over all possible configurations of this field phi. And in fact, I haven't really told you much about what this phi is, so I will say a few words about that. But ultimately, the challenge will be to sum over all the possible configurations. That's the difficult part. Expressing things as a path integral is of course very well known. But you can still ask, well, can we compute that integral? And of course, that's the main part. And going back to what this phi is, I just want to say a few words because I mentioned before that, of course, it's the interaction that really makes everything very complicated. And what we do when we use path integral is that we rewrite your point-like interaction. Here, you may imagine that you have spin up and spin down interacting by a point-like interaction. Then what we're doing when we use path integrals or field integrals is that we rewrite that as a field integral over particles going connected or interacting with an external field. So we're summing then over all possible values of this external field. That's what we're doing when we use this field representation of our system. In the systems that I'll be interested in here, I will be very much interested in point-like interactions, and that happens pretty much everywhere in condensed matter. But that's not the only situation you will have. Typically, well, I'm sorry, in that situation you will have auxiliary fields, but typically you will have a Coulomb interaction or a more complicated interaction like in QCD, and in that case, this phi will be either photons, in the case of the electromagnetic interaction, or gluons for QCD, and so on. So in that case, there's a real physical fields, and for the case I'm interested in here, this phi will simply be an auxiliary field. Now, once we have a representation where we can, we have to take one more step in order to even be able to imagine doing this massive integral, and that is we need to put these field integrals on the lattice. That is, our field here will be discretized in space and time, and so instead of phi of RT continuous variables, we'll now have discrete variables k, and that means that our integration measure now is a product over all those points on space-time, and there will be an integral associated with each point. And so we'll then have a finite, though large, number of integrals, and then the idea is that one would take that discretization to be finer and finer, and the mesh to be larger and larger in volume, and that then we will approach the continuum limit. So at the end of the game, one has to take the continuum limit. But at every step of the way, or at least as far as possible, one has this major upshot of this, that is that it fits in memory. So this field phi of RT is simply a function of one space-time variable, and so so the problem fits in memory, and we're not facing the situation that we faced before with wave functions. Now we have to face the other problem, which is, can we even do this integral? And for that purpose, we propose to use random numbers, because it's a very highly dimensional integral. And so that's what one would do. And that leads, of course, to lattice Monte Carlo, or to the computational implementation of lattice field theory, which is that in order to calculate the expectation value of your operator, you rewrite your field integral like this by identifying a weight, a normalized weight. And if that weight is positive, then you can go ahead and use random numbers depicted here with these dice to sample your field according to this weight. And once you have the samples, then you can compute expectation values of the quantity of interest and compute averages, and that's how you can do field theory. Now, this type of approach is, like I said, is lattice Monte Carlo, is quantum Monte Carlo, just generally speaking, or sometimes also called auxiliary field Monte Carlo. It's a rather general way of doing things, as long as this probability, or rather this weight, can be interpreted as a probability. But if you do have access to that, this can be a very, very powerful method. The types of systems that you can tackle are well known. The attractive Haber model, for example, without polarization, and if you have an even number of fermion species, 2 or 4, just even but not odd, then you can guarantee that there's a way to write that probability as a positive, well-defined probability. You can study graphene at the Dirac point, that is to say, tuned to the zero bias limit. You can study QCD at zero density, and you can study unpolarized neutral matter in the regimes that I mentioned before, close to unitarity, or even with a finite range. And you can study a variety of situations with ultra-cold atoms in specific regimes. For those systems, you can ask questions about the thermodynamics, phase transitions, static response, and other things that can be measured experimentally. And you can even calculate the entanglement entropy. In fact, together with one of my students, I helped solve some of the problems in calculating entanglement entropy using auxiliary field methods, like the one described here. ultimately leading to this to a formulation where you can write the nth order Renyi entanglement entropy as an expectation value using path integrals based on the algorithm by Tara and Grover from 2013. But in general, this is simply not possible. So in general, as many of you know, you simply cannot have a situation where the probability is nice and positive and well defined. In general, you will have a situation where the weight is complex. That's almost always true, and complex numbers are not ordered, and so we don't have really a well-defined probability that we can sample, and where we can determine which parts of the probability are most important. And that's crucial. You have to keep in mind that with these field integrals, the space that you're sampling is extremely high dimensional. It puts you in a position where if you're not close to the important parts of that integrand, then you're going to be very, very far away by any measure. And so that creates what we call a sign problem if your weight is complex, and that's nearly everywhere. It really affects a lot of problems across all of physics in condensed matter and high energy and nuclear physics. It affects high DC superconductors. So if you want to study a repulsive Haber model, there's been interest in that for decades, and that remains a very challenging system. If you want to study graphene at finite filling, so away from the direct point, that is in a way analogous to QCD at finite density, which you see here in this phase diagram, and that also has a sign problem. So not at zero density. If you are standing on this line, you can study the system at finite temperature, but if you want to turn on finite density, then you will be in trouble. And this, of course, is unfortunate because we're very interested in understanding the whole phase diagram from first principles using ab initio methods like lattice QCD, like this whole path integral formulation that I was telling you about before. We're interested in studying polarized neutrons. That also has a problem in nuclear matter as well. In part because of the interactions, but also because you have spin and isospin, and typically we'll be interested in situations that are not completely symmetric. So what can we do about this? This is, of course, a big problem, and it's a very interesting problem because it affects a variety of areas. So what can we do about the sign problem? And here's where I will really present a very skewed way of looking at things, because together with some of my students and colleagues, we recently wrote a review article where we presented what we like to call a taxonomy of ideas to tackle the sign problem. And I will not go over all of these. I will just mention a couple, but we subdivided them into new variables methods, statistical methods, and complex plane methods. And so just to mention a couple of these, the simplest idea one can try is really the idea of reweighting, which is to say, well, my probability is not really a probability, is simply a weight that takes positive and negative values, but let's consider the magnitude of that probability and sample according to the magnitude. So that will be, of course, positive, but then we can tack the phase onto the observable. And if you do that and you follow this chain of identities, you find that your expectation value can be written as a ratio of two expectation values, each of those determined with respect to the magnitude of the weight. And the top represents the observable with the phase, and the bottom is just the expectation value of the phase. The unfortunate situation here is that both the top and the bottom actually go to zero as you make the space-time volume larger and larger. That is to say, you have a 0 over 0 ratio where you're trying to determine the whatever's left from that as you take the limit of large volume and large space-time volume, and to try to determine this expectation value. So that's a really, really difficult problem that it becomes a noise problem, because both of these quantities are approach zero and they have a certain uncertainty around them. So that makes this noise problem manifest. So the sign problem is really, in this sense, a noise problem. Another approach that where we have pursued and other people have been pursuing, especially on the QCD side, is the idea of complex Langevin. And this is not a new idea. It's been around since the 80s, but it's recently been revived, especially on understanding the mathematics of it. And quite a bit of progress has been made. And in this case, what one does is one accepts the fact that this probability is complex in general, that the exponential of minus the action is complex, and that the action itself is complex, typically, and based on that, or motivated by that, one complexifies the field. And I will not say a lot more about this. I'll just say that if your field is already complex, then you have to complexify the real and imaginary parts, and then do the path integral or field integral in that complexified space. So this is the complexified field here. So I will show you some results obtained with this method in the next couple of slides. But that's all I want to say on the technical side. So the next 2 slides, then I will spend showing some selected results and then discussing a new idea that departs a little bit from this idea of stochastic methods and complex Langevin and such. To focus ideas, and as I mentioned before, I will be centered on this unitary limit of infinite scattering length and 0 range. And more specifically, I will be interested in understanding what happens at finite temperature and finite polarization at unitarity. And for that system, which does have a sign problem, together with some colleagues, we implemented a complex Langevin method, and we calculated the equation of state. That is the density versus chemical potential, and vary the polarization. And the result you see here, showing the density in units of the non-interacting density as a function of this quantity called beta mu, which is the inverse temperature times the chemical potential. So everything here is dimensionless. And shown here, you have in black the results from the MIT experiment from 2012, and that's an ultra-cold atom experiment. And the various symbols with various colors are the result of our complex Langevin calculations. And as you can see, at 0 polarization, our results agree very well with the experiment. They stop agreeing around this area, and that's why I stopped plotting them. So in the interest of full disclosure, I should say that past this point, there's still some disagreement that needs to be resolved, and most likely is on our side, on the theory side. But from beta mu equal to 1 and all the way to the left, things agree quite well. There's still some effects here, but not too concerning. The interesting thing that we achieved was that we were able to turn on the polarization. So we're able to turn beta h from 0 to 0.4, 0.8, and so on up to 2, and we obtain these results. And in the next few slides, I will compare these results with a different type of approach. And I want to remind you that this was obtained with complex Langevin. Is one of these approaches to solve the sign problem. And when thinking about methods to tackle this sign problem, together with my students, we decided to take a step back and consider that basically everything that's being proposed on that side of the story is entirely numerical solutions. There are, of course, approaches to the sign problem that are new variables approaches, where you try to rewrite the path integral entirely in terms of new variables and to solve the sign problem. And some of those are successful in some cases. But generally, when one thinks about Monte Carlo methods, one thinks about completely numerical solutions. And we realized that thinking about methods to solve the quantum many-body problem, or to calculate anything with many particles, one really thinks about these two things, these two limits, where the calculation is either completely numerical, or in another limit, you have something that's completely analytic, closed form, and actually small, a small expression typically. And we ask, is there nothing in between? More specifically, can we program a computer to do something completely analytic, but of a scale, or on a scale where humans can't really handle the problem? And so we started to work in that direction, and that's an idea that I will present next to tackle part of this many-body problem at unitarity. And to fix ideas, I'll just remind you that we're interested in thermodynamics. We're interested in the grand canonical ensemble, so this is a grand thermodynamic potential. And I will be focusing on interaction effects, and so I will consider the change in the thermodynamic potential, so the change in the pressure, if you want, which is given by the log of the ratio of partition functions, where z is the interacting partition function and z naught is the non-interacting one. And to tackle this problem, or the aspect of the problem rather that we were able to tackle, is the so-called virial expansion. This is a small fugacity expansion where the fugacity is e to the beta mu. And this Q1 here is the single particle partition function. So really, you should think about this simply as a volume factor. It's essentially this volume here. And the complicated part of the problem is calculating these virial coefficients. This delta bn's are the change in the what normally one would call the virial coefficient Bn relative to its non-interacting counterpart. And usually these are calculated by solving the n-body problem. So if these then depend on the n-body problem, what you would expect, which is in fact what happens, is that delta V2 is known exactly and has been known for a very long time. That is given in fact by the Beth-Uhlenbeck formula. But if you want delta V3 and beyond, this is typically much more challenging. There are some analytic approaches, but they are really tour de force. So they're very difficult. And usually this is done numerically. So a lot of the time when there's a new system, you find that delta V2 or the second order virial expansion is analyzed right away, but then it takes a while for people to get to delta V3, and to go beyond that is very, very challenging, in fact. And so let me tell you where the challenge comes from. And the challenge, in a way, or one way to see it is shown here. And I want to start with this equation here. The issue is that the nth order partition function scales the volume to the power n. And so how is that affecting the problem? That affects the problem in the following way. Delta V2, V3, V4, all these virial coefficients are volume independent. And so and Q1 scales like the volume. And so you see what should happen here is that the volume squared part should cancel in this difference between interacting and non-interacting. And you should be left only with the volume scaling part that will be canceled out with Q1. That's not very difficult to imagine. Is not a particularly difficult situation, but when you go to delta V3, this becomes more challenging. You see here, you have to cancel the third order in volume to be left with only the second order. Then the second order will be turned into a first order by this Q1, and then that will be subtracted from here, from that by this term, and you will be left only with the volume independent part. And so on and so forth. So every time you go to one more particle, you have to carefully subtract the volume squared cancellation, the volume, the volume part, the volume squared part, the volume part, and so on, to be left after this whole calculation with only the volume independent part. In other words, every time you add a particle, you have to be sensitive to the terms that scale not only with the volume to the power of number of particles, but everything after that. And that's very challenging to do. So the n-body problem will be challenging already by itself, but you really have to solve it with more and more precision as you go to higher and higher particle numbers. And that's why this is really, really difficult. And so to tackle this problem, we realized that we could not use quantum Monte Carlo, or at least we realized this would be very, very challenging to do. And we tried. And we only got so far. So we decided to do an entirely different approach where these cancellations happen explicitly and analytically. And to do that, we discretized time. So we follow this idea that you have to put your problem on a lattice somehow. In this case, actually, this happened because we realized that a good way to tackle the problem was given by this Trotter-Suzuki factorization. To calculate the partition functions that you need access to the exponential of minus beta times the Hamiltonian, and the main problem with this Hamiltonian is the kinetic and potential energy don't commute, of course. But if you separate them in this way, then you can then you have some access to solving the problem. In fact, what we were able to do is we're able to say, if in this expression you actually fix k and you compute for different values of k and take the limit after, then the intermediate steps actually can be computed. You can take your partition function for n particles and actually calculate it automatically, because if you put your expression in this form at fixed k, fixed order in this Trotter-Suzuki factorization, then all the integrals that you're left with are entirely Gaussian and can be completely automated, and that's how you can calculate delta Bn. This approach we began to understand a couple of years ago in a paper with Chris Schill, and then after that we started automating progressively more and more this calculation, and this culminated in this year with a sequence of papers with my student Yachiho and with Caitlin Morell and Casey Berger as well. And I will give you an idea in the next few slides of what we accomplished with this. And to give you an example, shown here is a calculation of delta B4, the fourth order change in the virial coefficient as a function of 1 over the order in the Trotter-Suzuki approximation. We did this for the unitary limit, and in order to fix the unitary limit, what we did is the calculation not only for delta V4, but also for delta V2. And then we tuned the coupling so delta V2 was fixed to 1 over square root of 2, which is its value, its exact value at unitarity as given by the Bethe-Uhlenbeck formula. What we obtained then was that as you increase K, you find a trend that seems to go towards the result of Jan and Blume, which they actually obtained by the Monte Carlo method with this relatively large error band. And so we set out to then improve our method to try to see if we actually agreed with them or where we ended up on this graph. And so here is the result of those explorations, which was published in this reference, and we were very happy that was selected for editor suggestion. And so this is a bit of a busy plot, so I will tell you what we're seeing here in steps. So he plotted here is delta Bn in the top panel, so the change in the nth order virial coefficient, and blue shows delta B3, red shows delta B4, and green shows delta B5, here with a minus sign to avoid interference. And by the way, on the horizontal axis, you have the essentially the coupling. So all the way at the left, you have vanishing coupling. So this is the free gas. So of course, no change in the virial coefficient when there's no interaction. And all the way to the right, you have the unitary limit. And what we were able to discern from our calculations was that we actually agreed with the lower end of this large error bar, which is the result of Jan and Blume, but we also agreed with the results of Endo and Castan, which were a conjecture, and the results of Campreticorn and colleagues. That was a diagrammatic approximation based on large range. The results that we obtained for delta V4, we generalized also for delta V5, and I skipped delta V3, but basically we agree with the exact results by Leirones. And going back to delta V5, this was the first prediction of the delta V5, the fifth order virial coefficient as a function of the coupling. And the interesting thing that we found was that it essentially is of the same size as delta V4. So it doesn't become smaller than delta V4 at unitarity. It is smaller than delta V4 if you move away from unitarity towards weaker couplings, but it's actually non-monotonic. And in fact, we analyzed this problem in more detail, and you can do that by looking at the subspaces. In each case, delta V3 has only one subspace where you have two particles and then of one type and one particle of the other type. But for delta V4, you have two subspaces, the 3-1 subspace, three particles of one type and one particle of the other type. And you have the 2-2 subspace, you have two particles of one type, two particles of the other type. And the same with delta V5, you have 4-1 and 3-2. And the interesting thing is that these subspace contributions come with different signs. 3-1 here is positive for delta V4, and 2-2 is negative. And so these two contributions get progressively more and more positive and more negative, and they partially cancel each other out, and so they compete, and that is what makes this calculation very difficult. And it's the same with delta V5. By the way, we were able to push our delta V3 calculations to order 21. So if we go back to the previous plot here, this was order 7. We were able to push order 21 for delta V3, and for delta V4, which was at 7, we were able to push it to order 12, and delta V5 to order 9. And based on those results, you obtain these curves that are actually extrapolations. So once we have all these results for the various virial coefficients, we can then try to extract some physics. And the first thing that we did is this slide that kept popping up that showed the density. It shows the density equation of state now reconstructed in the virial expansion as a function of the fugacity, and shown again with the same color coding as in the previous slide. That is third order. Actually, let me start with second order. Second order is the dashed line. Third order is the blue line with an arrow band. Fourth order is in red, and fifth order is in green. And in blue dots, as in previous slides, you have the MIT experiment. By the way, the dashed line for delta V4 is what you would obtain based on the previous determination, just the central value of the results of Jan and Blume. And we're very happy to see this, that basically when you go to fifth order, just doing the partial sums of the virial expansion up to that order, we obtain better agreement with the experiment than any previous virial expansion calculation. We went ahead with this, and now that we have the density, we decided to explore what happens when you look at a simple response function like the compressibility. And compressibility is shown here in units of its zero temperature non-interacting value, here shown as a function of temperature. And again, with the same color coding, we have the virial expansion. Blue is third order, red is fourth order, and green is fifth order. But we show more here. We, in fact, took those results and performed Padé resummations and Padé-Borel resummations. These are fits and to Padé approximants. And in the case of that says Borel here, we use a Padé-Borel transform as a resummation technique. And the results are really in fantastic agreement with all these other calculations and then the experiments. So the Luttinger Award results shown here in purple diamonds, the MIT experiment here shown in red circles, and complex Langevin results from the same reference I was telling you about before, shown here with black squares. So we were very happy to see this. Now, in none of these cases do you have a sign problem. So here, this system can be studied without sign problem. The system can also be studied without a sign problem. So both cases are really not very challenging from the point of view that I was explaining earlier in the talk. So what really is more interesting is to turn on some polarization. And thanks to the fact that we have these subspace coefficients, we can study the polarized system using the virial expansion with some kind of analytic control. And so that's what we did. And so in this slide here, I'm showing you now a comparison between complex Langevin results with the same color coding as I was showing you before, and now compare it with the virial expansion. And so then just to remind you, this is the density equation of state as a function of beta mu, so essentially the chemical potential in units of the inverse temperature. The bottom curve here is non-polarized, but then as you go to higher data sets, here in the graph, you see the polarized version. The various curves shown here, dash dotted, and solid, in each case are showing you the partial sums of the virial expansion, and the dashed line, sorry, the dotted line shown here and extended further towards higher beta mu is a result of a Padé approximant. And so you see that obtaining virial coefficients is actually useful. And its usefulness doesn't end over here where you would expect the virial expansion to fail, but actually it extends beyond that if you allow yourself to do a Padé resummation. So this is just one example. It needs to be explored further, and it gives us hope, and it makes us more excited about the possibility of computing even higher order virial coefficients. I will show you two more comparisons before concluding. Here is again the unpolarized case, focused on the virial regime, so the regime where the virial expansion is valid over here. And this is the comparison that was courtesy of Felix Werner, who sent me this plot a while back. And what you see here is the density, again, the density equation of state, but subtracting the third order virial coefficient, or third order virial expansion result. And dividing by the fugacity to the fourth power. And what you obtain, if you do that kind of plot, is that when you take the limit of fugacity going to 0, then you should converge to the result for the B4 coefficient. And that's what we were able to compare with the Endokan-Stan conjecture here, the various experiments from ENS and in Paris and from MIT, and so the Jan-Blume result. And this line here in green, this shows the result of my calculation with Yachi Ho that includes not only the fourth order, which agrees with the conjecture and seems to follow the same trend as this Monte Carlo data by Rossi and colleagues. Werner is one of those colleagues, by the way. But also we're showing the fifth order as well, which gives you a straight line. In fact, recently, we have pushed this method quite a bit. It's been a few months since our paper was published. And we're able now to push with some limitations, so with some qualifications, to ninth order. And the result of that is shown here. And this is the same type of graph, the same type of vertical axis and horizontal axis, but there's a lot of curves here, so I will unpack this for you before concluding. And you see here the fifth order, which is what I was showing in the previous slide in green. Here is in orange. And then you go to sixth order and seventh order, and you get these two curves down here. If you go to eighth order, you get this green line. And finally, ninth order, you get this this red line here. Now, as you go to higher and higher order, it gets more and more difficult to complete this calculation, and so you should keep in mind when you see this graph that as you go to higher and higher order, the accuracy of the calculation actually decreases. So we're confident on our results up to 7th order, but when you go to 8th and 9th order, then the result starts to deteriorate, and that means we still have systematic effects due to the coarseness of the temporal approximation. Nevertheless, you can go ahead and calculate the results of a Padé or Padé-Borel approximation. And if you perform that and you try to stay within as much as possible within the diagonal Padé approximants, for example, as shown in a previous slide, you can try to do a 2-3 or 2-2 or 3-3 Padé or Padé-Borel approximant. If you do that, then you will obtain these sets of curves over here, which actually agree remarkably well with the Monte Carlo results by Rossi and colleagues. So this remains unpublished, and so that's why it's simply showing you an advance of what we're able to do, and we hope to refine this and put out these calculations, and hopefully in the coming months. So I will then summarize and conclude. I think it's beyond any doubt for this crowd that quantum many-body physics is present at all scales and in nearly all areas in physics. Is a fantastic problem, but it's also a formidable problem from mathematical and computational standpoints. It's a problem of exponential memory requirements or exponential statistics requirements if you regard this as a sign problem, as a signal-to-noise problem. We have several methods that have been put forward to solve the sign problem, as I pointed out in our review article, and those can be classified as new variables methods, statistical methods, and complex plane methods. But what I try to put forward here towards the end is a new idea to bridge between entirely numerical and entirely analytic calculations. That is the idea that perhaps we can automate certain types of expansions and push them very, very, very far in a completely analytic way, but in a way such that computers can deal with the problem, whereas humans really wouldn't want to look at the massive amount of formulas that result from that. In our case, we use that idea to access the thermodynamics of strongly coupled matter in dilute regimes, specifically this universal regime of the unitary limit. And now we're pushing forward, looking to the future, continuously exploring new approaches and pushing this automated algebra methods to other physical situations, namely both gases and nuclear matter, but also other observables. You should keep in mind that the expansion that I've shown you, the virial expansion that I've shown you, is the simplest possible virial expansion, that one corresponding to the density and the pressure and the compressibility, but this can be generalized to other quantities as well. And of course, it will be a more challenging calculation, but there's no reason why one shouldn't be able to push to surprisingly high orders, given that we've been able to go to 9th order, as I've shown you in one of the last few slides, for the regular virial expansion. So I hope I convinced you then towards the end that going beyond 5th order in the virial expansion is not only possible, but also desirable, especially if you combine this with resummation methods. There are a lot of open questions about how to use those resummation methods and how rigorous they are, and those can and should be explored, and that remains an open problem. And with that, I will thank you for your attention if you got this far, and I look forward to seeing you in Trento next time, whenever we're all able to travel. Thank you.